Hi, in this video we will prove Kolmogorov's inequality, which will be a simple consequence of Doope's submartingale inequality, which we proved in the previous video. So let's see what it is about. We don't have a non-negative submartingales anymore. Rather, we have a sequence of random variables. We assume they are independent. We assume they are square integrable. And finally, we assume that their expectations are all 0. And then the inequality says that for each c, this looks very much like Doope's inequality, c squared, well, this looks similar to this, times the probability that the maximum of something is greater or equal than c, similar to this one, is bounded above by some expectations. So if you look at this formula, you can probably guess right now that what we will do, we will square both parts of this inequality here, and we will use this square thing as our submartingale to which we will apply Doope's inequality. This is indeed as simple as that, but before we write it down, let me explain why we need Kolmogorov's inequality. So I told you that one of our big goals for this week is to prove that under some conditions, this random series here, consisting of independent random variables, converges almost surely. How do we prove convergence of a series? We can say it is equivalent to the partial sums converging. We can also say this is equivalent to the sequence of partial sums being Cauchy. What does it mean to be Cauchy? It means that the difference between the nth partial sum and the mth partial sum should be small. Now, what does the difference between the mth partial sum and the nth partial sum look like? It is an expression of this form. I mean, the index will go not from 1 to n, it will go from m plus 1 to n, but otherwise it will be a sum of the random variables like this. And if we want to show it is small, and this is what we need for Cauchy, then we need some control on that sum being large. Basically, we will need to show that the probability of that is significantly small for it to never happen eventually. And this is what Kolmogorov's inequality does for us. Okay, so let's do the proof. So I will denote by Sn the sum of the first n random variables. Now, I claim it is a martingale. This is very simple. So it's integrable because all my random variables are square integrable. So integrable. It is adapted to the natural filtration. So we consider it with respect to the natural filtration. And most importantly, if I condition this whole thing on fn minus 1, then I will keep Sn minus 1. And since this guy is independent, I will replace it by its expectation, which is 0, right? So we have done it many times, so this should be clear. So this is a martingale. Now, my second claim is that Sn squared is a submartingale. Why? So this is a general claim. If a process is a martingale, then its square is a submartingale. So this can be proved by conditional Jensen's inequality. We proved it when we proved a long list of properties of conditional expectations. So this was the last property. It said that if we have a convex function, and here phi of x is x squared, and it is convex, then, okay, so let me just apply it. So what I want to show that this is greater or equal than Sn minus 1 squared. So this would prove that Sn squared is a submartingale. So I can write it in terms of my function phi, obviously. And then conditional Jensen said that this is always greater or equal. So conditional Jensen inequality. It is greater or equal than phi of the conditional expectation of Sn with respect to Fn minus 1. Now, since Sn is a martingale, this term is Sn minus 1, and phi is x squared. So the last thing is the equality. But between this and this, I have greater or equal. So Sn squared is a submartingale. So again, it's obviously adapted to the natural filtration, and it is integrable because Xn is square integrable. So now I will simply apply Dup's inequality to it. So C squared times the probability of the maximum of mod Sn, because this is just Sn, being greater or equal than C, is equal to, so as I said, I'm just going to square both sides of the inequality. Nothing will happen to them because they are non-negative. So C squared times the probability maximum Sn squared greater or equal than C squared. Now I have a non-negative submartingale, so Dup's inequality tells me it's less or equal than the expectation of Sn squared, right? Now Sn has expectation 0, right? Because it's just this, and the expectation of each x is 0. So this is simply the variance of Sn. We know if we have a sum of independent random variables, then the variance of the sum is equal to the sum of the variances. I here of the variances of xi, and this is the same as, maybe I'll just change it here, or even better just say, so this is the same as the expectation of xi squared because they all have mean 0. So this sum is exactly the one here, and this is the end of the proof.